of the B sub S to blah blah blah. The branching ratio is usually very small. Like this one, is the branching ratio is like 50%. Okay, so it's you can have a clear signal. Okay, you can accumulate enough events. But in the B sub S, the weak decay, the branching ratio is typically 10 to minus 3 or 10 to minus 4. Okay, so this is my reasoning. Is it correct?
Is that from the directly from this E to CC bar, or is from the B decays?
This is from the in B decay. It's a B sub S pi 0, and then D sub S decay followed by the D sub S decay, followed by weak decay to KK pi.
Yeah, but if you this from B decay is much easier.
Oh.
Because we produce a lot of B's.
Okay.
Right, and then it's clean. The background is smaller.
Okay. But they not in the E plus E minus.
In E plus we suffer from the combinatorials.
Okay. Anyway, they would be nice that LHCCP or will eventually measure the mass of the BS node and B node to test our prediction. So this means
it's difficult for LHCP. If you have a pi node in the final state, there's no way they can measure it.
Okay. So just 20 papers, but all the papers rule out except maybe the some number close to here. Okay, let me jump to the conclusion. So it turns out that near mass degeneracy of the scalar meson seems to be quite universal, because I mentioned that you will see the light one, the heavy one, or the Cheng meson one, and most likely also it will occur in the E meson sector. So it's a phenomenon is quite universal. And qualitatively, the near degeneracy can be understood in terms of the 7-energy diagrams. 7-energy diagram, due to the strong copy chain, will low down, will push down the mass. Okay. Now, quantitatively, the scalar meson can be deduced from the helical symmetry, supplemented from the Cheng meson spectral scheme, and we predict this number. And hopefully, it can be tested soon in the near future. Okay, thank you.
Okay, now is question time. Does anyone have any questions? Okay, Andy.
For your self-energy calculation, do you know if you do two-loop calculations that your equation will converge or not?
No, I didn't do two loop. One loop is already difficult. One loop is okay.
Is it possible that if you have two loops, you have increase instead of decrease?
But this is a kind of perturbation theory, so I don't worry about it. It must be converged. With convergence, will guarantee that the result will converge and go to the loop by loop, higher order loop. Because you have a cutoff like the moment of the Gaussian boson should be lighter than 1 GeV. There's a cutoff scale. So in principle, they should be converged. Okay, when you go to the higher loops. Result.
Can you tell if it will decrease also, or will not decrease it instead?
I don't know which direction it will head to, but even for the one loop calculation, I just mentioned before that for one loop calculation, it's just a lot of uncertainties here. You don't know what's the Bell mass, you don't know that. We don't calculate the contribution from year to year, from those one plus actual factor Meson contribution, also factor Meson contribution. And the more serious one is the problem with the emerging scale. So I mean, it seems to me it doesn't make too much sense to go to the beyond one loop calculation, because even one loop you now have good handle. So I would say to the best, I think it's just considered here. This is just a qualitative statement rather than the quantitative predictions.
Professor Zhao?
In your first calculation using the heavy pop symmetry on the mass of the DTO. Okay, that was a overshoot. Okay, because
Yes.
and that one you use the here, right, DSU. Okay, DSU. Okay, and here's overshoot. Okay, and because you have used the heavy pop symmetry in the pop propagator, and now if you use the relativistic pop propagator, then these are improved. I mean, much better.
Yeah.
Okay. So that implies what? Implies the charm pop. I mean, is not so. I mean,
Not heavy enough.
Yeah, not heavy enough.
Not heavy enough. Wall range is not small enough.
Okay. Now you use the near mass degeneracy. Okay. To predict the near mass degeneracy of the B sector. Okay. Then I don't know how.
Okay, but it's a different. It's not calculation. It's just those are input for experimental.
Yeah.
So I don't calculate those one.
Oh, okay. So you.
I don't do that. I just experimental input.
Okay.
It's a experimental spectroscopy for the Chinese. So it's input. So I don't worry. Then of course I don't worry about what is the correction or when correction, QCD correction. So I think it's a scenario is much better than the quadruple calculation, which actually is not so trustworthy.
So far you only discussed the scalar, okay?
Yeah.
Near mass degenerate scalar, but then for the pseudo scalar, we know they are split by about 100 MeV, and also for the vector, and also for the pseudo vector is about 30 or 40 MeV. Okay, can you all explain this?
Oh, come on, give me time.
But
I cannot do.
You see,
everything.
you can explain the degeneracy, but you should also explain the non-degeneracy, right?
Sure. In fact, the next step we try to do
With the same framework. Otherwise, this is not.
Sure. Next step we are going to understand what the B sub S BS1 and also DS1. The mass of the DS1 BS1.
Well, I can tell you, okay, in my calculation, okay, just in one shot, okay, all the entire spectrum coming out, okay, correctly.
Okay. This is not obvious.
Rather than just look at the scalar and then cope up with some calculation, and maybe in your next calculation, maybe 4 different procedures.
I'll try not to do that.
Any other questions? Okay.
I'm not so familiar with the heavy metal calculus research. I'm curious about when you calculate the loop diagram, do you have divergence?
Yes.
So how to cancel the divergence?
Okay. So we normally use a dimension organization. Okay. You have 1 over 0 term. Okay. Plus log 4 pi blah blah blah. Okay. Those terms you just saw away because it will be absorbed by the counter terms.
Yeah. So
The counter term is something like the mass term.
Yeah.
Like a master. It will be there.
Usually people will introduce counter terms to
Yeah.
cancel the
Yes.
divergence.
Yes.
Then another question is how to determine the coupling of these counter terms. So do you,
Let's,
since you're
yeah. You have to. I didn't do the real calculation about the counter. I just saw away, okay, but because I know it's the same. But how to determine the coefficient of the counter term? Actually, it should be appeared to the experimental measurement. That's the spirit of Heidelberg theory. Heidelberg, when you go to the higher order, you allow the coefficient. Those are model independent, but in principle, you don't know how to get it. In principle, you can do some model calculation to estimate those coefficients. But by the end of the day, you have to use the experimental measurement to determine those coefficients.
Any more? Okay, now let's thank Mr. Hayang again.
Thank you.